All right, well, welcome to our second to last meeting for this class. That's it, man. We've got today, we got Friday of this week, and then a final exam. And so again, the plan today is I'm going to talk about Stokes Theorem, the last of the theorems that tie these integrals together. And then on Friday, we'll go over the quiz and homework, stuff like that, and then finish up any last bit about Stokes Theorem, if there is any, and then we'll spend the rest of the time reviewing. So definitely the home stretch. You should be able to see that finish line. It's coming real soon. So in terms of homework questions, I know Eduardo already has a couple he'd like to look at. He says he'd like to look at numbers 4 and 5 on section 6.8. Are there any others that people want to see? All right, well then let me go ahead and share my screen and we'll go find those guys and take a look at them. So we should have an over under on how long it takes for my computer to actually get where we need to go. Or if it even works. This morning in calculus class, my computer completely just like bailed on me as I was trying to look up homework sets. So we'll see how this goes. All right, you know what I'm gonna do? I'm gonna stop sharing. And how about this, Eduardo? Can you maybe tell me, read them to me, or put it in the chat box what we're trying to do? I'm still going to try to pull this up, but
I can pull it up real quick.
oh, ratio.
All right, so it's number 4 is use the divergence theorem to compute the flux on the field, and then for the vector, the x component is 3y e to the z, the y component is 25xz, and the z component is 1 over the square root of x squared plus y squared, arctangent, and inside the parentheses is z over the square root of x squared plus y squared. And then it says out of the region E that lies between the spheres, x squared plus y squared plus z squared equals 9, and x squared plus y squared plus z squared equals 25 in the first octant.
Okay, everybody get that? Okay, good news is I was able to get it up while he was reading that. So thanks for buying me a little bit of time. I went not through Canvas. I think it's maybe Canvas that's being the issue. So can everybody see it? You see my screen?
Yeah.
Yeah, we're good. Okay. So here was that one that Eduardo read to us. So first of all, let's think about the divergence theorem and whether or not we can use it. So for the divergence theorem, what do you need?
A closed surface.
Okay, so it needs to be a closed surface, it needs to be a piecewise closed, piecewise smooth closed surface. And so let's think about what they're talking about. We've got a region that lies between these two spheres in the first octant. All right, so is that going to be a closed surface? Can you even visualize what it looks like?
Yes.
So just think about like the shell of a basketball or something like that, right? And then we're just cutting that basketball into 8s and we're just looking at one little piece of it. So in terms of the surfaces, there's the outer sphere and the inner sphere, and then the little planes that connect the edges, that gives it the thickness. Okay, so we're definitely good to dive in with the divergence theorem. All right, so let's get the divergence. What's the divergence of this? How do you calculate divergence?
It's the partial derivatives of each component.
Okay, so we're just going to take the partials with respect to x, then y, then z, right? And add them up. So it's sort of like a dot product-y kind of thing. So before I go to the whiteboard, let's just look at this. So the first one, the 3y e to the z, its derivative with respect to x is going to be 0. The 25xz, its derivative with respect to y is 0. And this guy, the derivative with respect to z, that one we're going to have to do. So let me just go ahead and write this guy real quick so that we can go catch its derivative. And yeah, all right, so let's go to the whiteboard. All righty. So we're doing goodness gracious. We're doing a partial with respect to z of 1 over square root of x squared plus y squared times inverse tangent of z over square root of x squared plus y squared. All right, so we're differentiating this guy. So the 1 over square root of x squared plus y squared is a constant, so it just goes along for the ride. Inverse tangent, its derivative is 1 over 1 plus this thing squared times the derivative of what's inside. And the derivative of what's inside there is 1 over the square root of x squared plus y squared. So that came from the chain rule, right? These two pieces came from the chain rule on the derivative, and then this was just the why am I spacing here? Constant multiple. Jesus. All right, so there's the derivative. Let's simplify it. These first and last things just give us an x squared plus y squared on the bottom, which then if I distribute through, just gives me a 1 over x squared plus y squared plus z squared. The x squared plus y squared comes from multiplying it by 1, and then it cancels with the denominator here to give us z squared. So this right here, this is the divergence of f. All right, so before we move on, we good with that? Any questions on the divergence? All right, so it looks like we're good. So now let's think about the divergence theorem. In order to get this flux, right, we know that the flux over the surface is the same as the triple integral over the region of the divergence of f. Okay, so we're going to be integrating then over this region 1 over x squared plus y squared plus z squared. So now we just got to see if we can get our bounds and figure that all out. All right, so thoughts and suggestions. What do you think we should do here?
I did spherical coordinates on this guy.
That is absolutely the right move. This is dying for spherical. Specifically, think about the region, right? That region in terms of spherical is going to be just have constant bounds. The rows are going to go from, I think it was 3 to 5, right? Because remember our spheres, we were between the ones given by x squared plus y squared plus z squared equals 9 and x squared plus y squared plus z squared equals 25. So that's going to be bounds from 3 to 5 on our row. Our theta since we're in the first quadrant, it's just going to be 0 to pi over 2. And our phi, because we're in the first octant, is going to be from 0 to pi over 2. So I love the idea of going to spherical. So if we go to spherical, first of all, change this function. What does this look like in terms of spherical coordinates?
1 over rho squared.
Cool. 1 over rho squared. We do need to put in our Jacobian for spherical. So what's the Jacobian?
Rho squared sine phi.
All right. So good with that?
Yep.
Okay. And then we're going to have d rho, d phi, d theta, let's just say. We'll go in that order. So the rows are going to go from 3 to 5. The phis are going to go from 0 to pi over 2. Because again, remember that's from the positive z-axis rotating down. And so since we're in the first octant, that's where x, y, and z are all positive, then we stop at pi over 2. And then our thetas are also 0 to pi over 2. And this ends up being super nice because those rho squareds cancel. So we're just integrating sine of phi. All right, so yeah, at this point, you just do your thing and you get your values.
So I have a quick question.
Yeah,
We're not getting 0 to 2 pi on our thetas because we're not getting negative values, correct? We're only getting positive values.
because I think they told us we were first octant. And
Yeah.
that just means that's, yeah, where X, Y, and Z are all positives.
Yeah, that's where I was getting stuck on because I got everything else the same. I just, the last bound on theta, that's where I couldn't figure it out what was the top bound.
Okay. Anyway, so there you go. And at this point, I'll let you do it. It should be pretty easy.
Yeah, I could figure it out. I got it.
I think you get pi, I think. I don't know, but that's what I'm going to say we get until you guys prove me otherwise. All right, so cool for that one. But you can see why this is nice. Let me go back. We're going to want to go look at the next one again anyway, but let's just go back at this and let's think about what we would have had to do otherwise. In order to find the flux, we would have had to do an integral, a flux integral for each surface, each of the pieces that make this up. So that's not just the two spheres, right? But we'd have to do it over the two spheres. But then we'd also have to do 3 more surfaces that are planar, but like chunks of rings, right? That'd be where the different planes, coordinate planes intersect the sphere. So this would actually require 5 different surface integrals. We'd have to parameterize each one of them. Now, some of them are easy, like those little like or the little circular strips, the arc strips. Their normal vectors are going to be really easy because they're in the coordinate planes, right? So you're talking about things like 1, 0, 0, 0, 1, 0, things like that. So those are going to be pretty easy. But then think about what we do. We would take those normal vectors and dot them with this field and then integrate over the region. And some of these are going to be nasty, nasty, nasty things that we have to end up integrating. So the divergence theorem definitely helps us out here. All right. So then the other one you asked about was number 5. Was that correct, Eduardo? The very next one?
Yeah.
Okay. So let's look at this guy. So it says let V equal blah, 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 be the velocity field of a fluid. Okay, so it's a velocity field, it's still a field. Compute the flux across the surface, x squared plus y squared plus z squared equals 1, where y is greater than 0, and the surface is oriented away from the origin. All right, so what does that look like? All right, good. So Victor just put in the chat, it is a sphere. So it's a sphere of radius 1. And then it says where y is greater than 0. So what we're actually looking at is a hemisphere, right? We're just looking at half of that sphere. And it said, okay, so hint, use the divergence theorem. You should have a slight problem with that. What's the problem with trying to just dive in and use the divergence theorem?
Don't we get 0
Yeah, I got 0 when I used it.
for the partials for each component?
I don't know that that's necessarily going to be a problem. That's not the problem I'm saying. I haven't, to be honest, I haven't even looked at what the partials are going to look like. There's a fundamental issue with trying to use the divergence theorem here. Yeah, thanks, Victor. He just put it in the chat box. It's not closed. This isn't a closed surface. This is just a hemisphere. So we can't technically use the divergence theorem here. So then the question is, well, why did they just say, hey, use the divergence theorem? Yeah, Victor's got it. We're just sucker off. Let's actually close it with a disk, a planar disk, so that we now do have a closed region, right? So it's going to be our hemisphere and then the disk at the bottom that turn it so it's in the y direction. But then it is closed and we can do the. However, that's not going to give us the flux over the hemisphere. That's going to give us the total flux. So what are we going to have to do to then figure out the flux of the hemisphere?
Would we have to divide it by the area or the volume of it? Half of the volume?
No, we're not going to divide anything. Okay, thanks, Jesus. You just said we're going to subtract. What we'll do is we'll just subtract the flux for the plane. So basically what we're doing here is we're trading finding the flux over the hemisphere for finding the flux over the plane. Because we're still going to have to do a flux integral. It's going to be a lot easier to do that flux integral for the planar region. And then we can take that away from what we get with the divergence theorem. So this is just one of those tricks. You put something in to make it be nice. In this case, make it so that we can use the divergence theorem. But then we have to remember to take it back out. By this point in your mathematical careers, you've seen this so many times in various forms that hopefully it doesn't really catch you by surprise anymore. If anything, you should just be like, yeah, that sounds about right. It's a very mathematician-y thing to do. Okay, so let's go to the whiteboard and let's see if we can knock this sucker out. So let me clear all that other stuff out of the way. All right, so basically here's our picture. I'll try to make it so that it's going in the right direction. Pretend that that's spherical, not not an elliptic paraboloid. Let's see how this looks once I take the other piece away. Yeah, better. Okay, so there's our hemisphere. And so y is, if you want to see what the axes are doing, I've got it oriented this way, x, y, z. Okay. So we've got outwardly pointing whatever, but if we close it off with that little bit there, now we can use the divergence theorem. So let's get the divergence, the divergence of f. If you go back and you look at that, it was a 2xz minus 2xz minus 3 plus x squared plus 3 minus x squared, which many of you told me was actually 0. Okay, so we get that the total divergence here is 0. Ooh, what does that tell you about this thing? What do we call a field whose divergence is 0?
Source free.
Yep, it's source free. So we know that for any enclosed thing, the total flux is 0, right? So we know that the flux over the closed is 0. You integrate 0 over this region, you get 0. Okay, but the flux over the closed is the flux over the hemisphere plus the flux over the disk. So we need to calculate the flux over the disk. So here's our disk. We need the vector to be pointing to the left, because we want to have outwardly pointing vectors. In fact, right, didn't it say that the arrows were pointing away from the origin? So if they're pointing away from the origin on the hemisphere, that means they're pointing this way. So they're pointing outward, which means they got to be pointing outward, which is to the left. Okay, so what's that vector for the disk? Yeah, it is normal, but can you give me the coordinates?
Zero, negative
really
1, 0.
Beautiful. Yeah, it's a really, really easy one. It's just 0, negative 1, 0. Because it's only pointing in the y direction and it's going that way. Okay, so let's calculate the flux. All right, so we've got a double integral over our surface. We're going to do f dot n. All right, so if we go back to our original and dot it with this, we get negative 5 plus 2xyz plus 3y minus x squared y. And we're going to integrate that over the surface. Now, this surface is planar. This is just a regular old double integral. Even better, we can simplify this. Because this piece right here is it's on the xz plane, right? What's the coordinate of the xz plane? or what's the equation of the xz plane? Yeah, it's just y equals 0. Which means we can put 0 in here for all our y's. By doing that, this becomes a double integral of the region minus 5 dA. Which of course means this is -5 times its area. And what's the integral?
Pi r squared.
Okay, so pi r squared, and the r is 1 for this sphere. So that's minus 5 pi. So like I said, we still had to calculate a flux integral. It's just this flux integral was crazy easy. All right, so what's the flux over the surface we were given then?
It's -5 pi.
And it's not -5 pi. -5 pi was over the planar circle. It's actually going to be a positive 5 pi, like Hazy's just put in the chat, because they have to add up to 0, right? Remember, we know that if we enclose this, the total flux is going to be 0. So if there's -5 going this way, it means there has to be +5 going the other. So the flux over the hemisphere then is a positive 5 pi. All right, so this is actually a technique you can do anytime. You can absolutely do this anytime. If you want to get the flux over a surface and want to use the divergence theorem, you just have to close it off. And I use just this circle, right, this planar circle disk to close it off, but I could have like done the entire sphere and then subtracted off the left-hand side. I could have put on the other end there a cone. I mean, I have all kinds of choices. But if you do this, you want to pick a surface that's easy to calculate the flux through, right? Because we're still going to be doing a flux integral. Just make it so that it's a nice, easy one. And this one was nice because since it was one of the coordinate planes, one of our variables went away. And it took a lot of other stuff with it. Anyway. So is that better for this one? Make a little more sense?
Yeah, thank you, Bruce.
Yeah, you're welcome. Oh, mathematicians and their crazy little tricks. The more math you do, the more you see these things, the more you start just doing them. And I think that, you know, I know a lot of times you guys see me do stuff and you're like, man, how do you know to do that? And it's purely, I've seen the tricks before. I've been trained to think that way. I've been trained to figure out, ooh, what's the easy way to get around it? And the divergence theorem is easy. Easy. So if you can make use of it, do it. All right. So any other homeworks? We could move on. All right. Well, then just give me 1 second here and I'll switch to the whiteboard. So I will see you in just a moment. that was a close one. As I was moving my stuff, one of my cords cut my high quality root beer and it almost knocked over. I would have had a major sad face. So, whew. All right. So, last theorem of the quarter. This is it. Once we get this one down, we're good to go. This one's called Stokes Theorem and named after English mathematician who came up with it. And Stokes Theorem, what it does is it relates surface integrals to line integrals. So you think about all the other things that we've done so far. Green's theorem, well, that turned line integrals into double integrals, or it related those two. Divergence theorem, similar, took a surface integral and related it to a triple integral. Well, this is now going to link line integrals and surface integrals. All right, so here's the deal with Stokes theorem. First, we got to talk about what you need, right? What do you actually need in order to do Stokes theorem? So for Stokes theorem, we need to have a surface. Okay, so we're going to have a smooth surface with a boundary curve C. Okay, so you can think about, for example, think about the one that we were just looking at, where we had that hemisphere, right? So that hemisphere was S. Its boundary curve was that circle, right? That was the edge of the surface, was that circle. So that's this guy C. All right, so we've got a boundary with our surface. And then the other thing that we need is that this curve C is oriented positively So we'll talk a little bit about this because now positive orientation doesn't necessarily mean clockwise or counterclockwise, because if we've got the surface in space, our curve's not even in the plane. It's not even necessarily a plane in a plane, period, right? So clockwise, counterclockwise doesn't really work anymore, but we'll talk about what that means in just a second. Okay, so this is all you need. You need a smooth, it needs to be simply connected. I should maybe put that in there too. And that this curve is closed. So I'm going to put here positively oriented and closed. Okay, so this isn't going to work for something that just gives us a boundary that's like a line or something like that. It actually has to be a closed curve. All right, so that's all we need in that regard. Then if F has continuous partials, so our field has to be nice enough that it's got continuous partials, then what we get is that the integral over the curve of f dr, so we just have our line integral, it's actually the same as the double integral over the surface of the curl of f dotted with ds. So we now have a link between a line integral and a surface integral. All right,
Cool.
so let's just kind of talk about what this means and what this says. Go ahead, Bradley. I see you're about to say something.
I was just saying that's kind of cool how this is all playing together.
I'm sorry, say that again.
It's kind of cool how all this is coming together.
Yeah, it's pretty amazing how all these very different things are actually related to each other. It's almost as if there's some sort of like fundamental framework to mathematics. Huh. Yeah, probably. But yeah, it is kind of cool that now that they come together. Okay, now I will say that this is maybe the least intuitive of the theorems. Like the other ones, when we prove them, you can definitely see where the proofs go. You can prove this as well. But even when you go beyond that and you start kind of talking about some of the ideas behind it, like the divergence theorem, it kind of makes sense that divergence is related to flux, right? I mean, yeah. This one's maybe not quite as intuitive, that curl of a field is actually related to, well, this is just like a work integral. But if you kind of think about it, it sort of makes sense. So think about curl. Curl is all about the ability for a field to do rotation. So why wouldn't that have something to do with work on a closed path, right? You're getting kind of rotated around. All right, but this is where this gets really interesting, is notice that this surface and this boundary, it doesn't say how the surface looks other than at the boundary. And so you could actually have different surfaces that all share the same boundary curve, and they're all going to end up getting the same curl if you integrate over that surface. And to me, that kind of blows my mind. Like, go back to that idea of the circle, right? So let's say that this is our boundary curve C. So think about all the different kinds of surfaces that have that same boundary curve. We could go with a hemisphere. We could go with an elliptic parabola. We could go with a hyperboloid. We could go with a cone. We could go with just the disk, right? All of those are very different surfaces. And yet, if you were to integrate the curl over the entire of the surface, you're going to get the same thing every time. And to me, that's kind of mind-blowing, right? That all that matters is the edge of this thing. It doesn't actually matter what the surface is. So the reason that this is actually a nice theorem is it makes it so that we can take some really gnarly surface, and instead of dealing with its surface integral, we just look at its boundary. Or alternatively, let's say we want to do some sort of a line integral, but the field is such that doing this integral is kind of a pain. But then we can find its curl, and maybe its curl is nice, and just turn it into a simple surface integral. And if you are going to do this, pick a nice surface. I usually pick a planar surface, if possible, right? Because then that's pretty easy. All right, so this is kind of a trippy idea, but it definitely holds out. Now, let's talk a little bit more about the positive orientation and close, because now we actually have two orientations going on. We've got the orientation of the surface, right? We got to think about which direction is our normal vector going. And then we have to worry about the orientation on the curve. Okay, so here's how you determine positive or negative relative to the normal vectors. You're going to use your right hand. This is another right hand rule thing. And what you want to think about is, suppose that the normal vector is sticking out of the surface. Okay, so here's our normal vector. What you're going to want to do is you're going to want to take your right hand and wrap it around and grab that normal vector. Okay. So notice my fingers as I wrap around that are curving. This is positive orientation. All right, so That's what it means to have positive orientation. So let's just go back to how we talked about positive versus negative orientation of curves in the plane, right? So here was a curve in the XY plane. And which way did I tell you was positive orientation?
Counterclockwise.
Okay, so it's going to be counterclockwise. So in the case of this, it's going to be counterclockwise. For the Victor just put upward, that's for orientation of the surface, was upward or downward. But this is just for the curve itself. So we were taught, I told you, I taught you that for this to have positive orientation, we need to be going around in a counterclockwise direction. Okay, well, let's think about the positively oriented normal vector. So the positively oriented normal vector here, it's going to be going towards positive z, which is towards you, right? So here's our normal vector coming towards you. Now I take my right hand and I go and reach around it to grab it, right? Look at how I'm curling my fingers. So this is the orientation of positive curve for that surface. And if we come back, you see, yeah, that's counterclockwise. So when I told you, hey, we want this to be counterclockwise for it to be positive, that was so that it was going to match up with orientation with normal vectors to surfaces now. Okay, so and what's really beautiful is that positive versus negative, it all really kind of depends on your perspective, but it really depends on the orientation of the surface itself. So if we had gone with downward orientation, so that the vector is pointing this way, my right hand goes to grab it, right? And your thumb always has to be going towards the positive. I go and I grab it. Now my fingers are going the opposite direction. And so positive orientation to a negatively oriented surface is going to be the other direction. But now just turn yourself around. Imagine you're behind the whiteboard. You see this, and that would be positive orientation to you back there. So it is consistent. It's absolutely consistent. It doesn't matter how you define your n. It doesn't matter how you define it. Positive is still going to make you go the same direction, depending upon which side you're on. So grab your normal vector with your thumb pointing in the positive direction of it. Wrap your fingers around, and that will tell you positive orientation. Okay, but we need to have that for this to work. If we don't, if we say we have negative orientation, you know what's going to happen. What happens if we have negative orientation as opposed to positive? Yeah, there's a sign change. So this isn't going to be true if you're not positively oriented. They're going to be opposites of each other. But this is the process. All right, so this is another theorem I'm not going to prove to you because the proof of this one is pretty gross. You can see it in the book. They kind of walk you through it. Basically, you break the surface up into a bunch of little chunks and look at the curl on all of them, and then you see that some of the curl cancels with other parts of the curl. And we're not going to go there. I just want to show you how it's used. Just want to show you how it's used so you can see the benefits of it and how we use it in both directions. Okay, because this is another one where sometimes you want to do the line integral instead of the surface integral, and vice versa. All right. Okay, so in terms of an example, how about we try this guy? So let's calculate the double integral of the curl of f ds, where f is given by z squared minus 3xy x cubed y cubed and s is the part of z equals 5 minus x squared minus y squared. That's above z equals 1. All right, so first of all, just that surface. It's elliptic paraboloid. It's a bowl. It's an upside down bowl. And we're just looking at the part that's above z equals 1. So what we're actually trying to calculate then is this surface integral of the curl of this. So we're basically adding up the total curl over the entire surface. So how much rotation is happening along the surface, right? That's what this is asking. All right, so if we wanted to do this just without Stokes theorem, we could. You can calculate the curl of this, right? We can take the partials, get the curl. Then we can find, we have to parameterize this surface. That's not that big of a deal, right? Parameterize that surface, get the normal vector dotted, blah, 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 integrate. Okay, we can do that. But alternatively, watch how fast this is if we use Stokes theorem. All right, so first of all, let's think about the boundary curve. What is the boundary curve to this surface? Can you visualize what it looks like?
Wouldn't it be a disk?
Okay, so it is a disk. It's a circle. It's a circle. This thing, because this shape, what it looks like is this, right? It's the bowl that's been turned upside down. And so it's this circle down here. That's our C. Let me erase the orientation. We'll see if we can figure out what the orientation should look like. Okay, so that's what C is. It's a circle. And in fact, the equation of the circle is going to be where that intersects z equals 1. So it's a circle of radius 2 that's centered at the origin. Okay, so which way is it oriented? Now, we do need to know the orientation of the surface, and let's just assume that it's positively oriented, right? Upward pointing normal vectors. So if I've got that normal vector pointing up, I go and I grab it. My fingers are rotating this way. So the orientation of this curve is kind of like how I had it written originally. There's our orientation.
Do we use normal vectors with respect to the whole surface or to the circle?
Yes. You don't want to think about it at the boundary, because at the boundary you don't necessarily know. You know what I mean? Like, because it's a line. Because it's now just 2-dimensional and not 3-dimensional. But basically, you just kind of want to go with the in general for this surface. So if it's upwardly pointing, thumbs up. Downwardly pointing, thumbs down. Best way to think about it. Does that kind of make sense?
Yeah, that makes sense. Thank you.
Okay. All right, so let's think about this line integral. How do you feel about doing this line integral of f dot dr if this is our curve?
I'm down.
You should feel pretty good about it, right? How many times have we done one of those where we've gone around in a circle? Oh, Jesus, forever, right? So it's actually going to be pretty easy to parameterize that circle, right? So let's do that. Let's actually find this line integral for that closed curve. All right, so let's parameterize it. R for the curve, since it's a circle, we're just going to do r cosine and r sine. The r is 2. So let's make this 2 cosine t, 2 sine t. Oh, but we also need a z component.
0.
Not 0, but you're thinking right. What is the z for that circle? There you go, Seamus just put it in there. It's 1, right? Remember, this was where we intersected z equals 1. So this is going to be our parameterization for that curve. And we'll let the t's go from 0 to 2 pi. All right, so for the line integral, we need an r prime. All right, well, that's minus 2 sine, 2 cosine, 0. And then for that line integral, this is now going to be the integral from 0 to 2 pi. And we just have to take f and dot it with r prime. So this is going to give us z squared times minus 2 sine t. And we're going to get minus 3xy times 2 cosine t plus 0. All right, but now we need to replace the z's, the x's, and the y's. But we're just going to use our components from up here. So z was equal to 1. So that's just going to be a minus 2 sine t. X and y, multiply those together, we're going to get 4 cosine times sine times another 6 gives us minus 24 cosine squared times sine. All right, well, that's what that line integral looks like. And this sucker is easy enough to put into your technology, or if you want to do it by hand, it's actually not that bad. James, you just said this is ugly? Oh, you're killing me, man. Check it out, 2 sine. Its integral, 2 cosine. You're weak with integrals now? Okay. So this is just 2 cosine, no problem. Plug in your 2 pi and your 0. This one, you could do a u substitution. U equals cosine, then du is sine. Real easy u sub. You end up getting, I think, cosine, like 8 cosine cubed or something like that. So then we can plug in our 2 pi and our 0. And I'm pretty sure, just did this in my head, and I think it's equal to 0. Punch it into your favorite technology and see if your technology's brain is better than mine. Okay, so we were able to calculate this surface integral. I mean, it's the flux of the curl through the surface. But we were able to do that with just a line integral. Try it the other way, just for fun. We're not going to do it right now. But calculate the curl of f first. right? Go through the process with your partials and the determinant business, and find that curl. Then parameterize the surface. Then do that, and you'll see that this is much faster and much easier. Okay, so this is an example of where you want to make use of the line integral to take care of your double integral, your surface integral. But there are other times where you want to do it the other way around, where you'd much rather use the line integral to actually, the curl, the surface integral, to actually do the line integral. And I want to show you an example of that next, but let me answer any other questions on this one.
What does it mean to get a 0 value in this instance again?
Okay, so a 0 here, well, it depends which way we want to think about it. As the line integral form is saying that there was no work done over that loop. So as a particle is getting moved by this field around that circle, a total of 0 work was done. That doesn't necessarily mean that it was a conservative vector field, and in fact, it's not. Right? You can still get 0 over a closed loop even if it's not a conservative vector field. It's just you're not guaranteed that. So in terms of the line integral, that's what it means. In terms of the surface integral, it means that there's no flux, that the curl of F, the field that is the curl of F, that there is no flux over that, which basically means there is no rotation, like the net rotation over that surface is 0. So that's what that would mean in that regard. Good question. Other questions? Okay, so let me show you an example now where we actually want to do the surface integral instead of the line integral. All right, so here's what we're going to do. We're going to find the integral of f dotted with dr, where f is given by z squared y squared x, and c is the triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we're going to go ahead and go with counterclockwise orientation. So we'll go with the usual orientation. So this is actually a problem I could have given you on the last exam where we were doing line integrals, right? I mean, it's basically, here are your coordinate axes, and we're doing those 3 points. So we got a triangle, and we're going around in counterclockwise direction, right? So think about what this would require if we're just going to do line integrals. It's going to require 3 integrals, first of all. 1 for each side of this triangle. And so for each of those 3 line integrals, you're going to have to parameterize the lines, do your thing, right? Add them up. Okay, instead, let me show you how fast Stokes theorem can be. All right, so what we need to do is first calculate the curl of F. Okay, so for the curl of F, I, J, K, dx, dy, dz, and then we've got our z squared, y squared, x. All right, so the curl of F, we're going to get the derivative of x with respect to y, which is 0, the derivative of y squared with respect to z, which is 0. For the j component, the derivative with respect to z of z squared, so that's 2z. The derivative of x with respect to x is 1, so 2z minus 1. And then the y component, the derivative of y squared with respect to x is 0. Z squared with respect to y is 0. So there's our curl. Okay, so the curl vector is pretty easy. But now we need to do the surface integral. So this says, or if we're using Stokes theorem, we can use any surface that's got this triangle as a boundary. So I'm going to pick the plane that holds that surface, that holds that triangle. Okay, so this is going to be my surface. It's going to be a plane, and the equation of that plane is going to be x plus y plus z equals 1. So the way I got it was just, well, because I saw that if you add up all three of those, you just always get 1. So there's the equation. But you can always do the whole find two vectors, cross them, whatever business. But there's that plane. All right, so that means I need a normal vector for it. So can you give me a normal vector for it?
Wouldn't that be 1, 1, 1?
That totally works. 1, 1, 1. All right, so normal vector is 1, 1, 1. Remember, you can just read the coefficients off of those guys, x, y, z. All right, so cool. This now means that we're going to be integrating over our surface the dot product of those, which is 2z minus 1. Well, let's turn this into a regular double integral, because I can solve this guy for z. It's z equals 1 minus x minus y. So if I fire that in here, this is now a double integral of 1 minus 2x minus 2y. And in terms of the bounds of x and y, if you look in the xy plane, this is a triangle. That connects those points 0, 1. So let's do this dy dx. The y's, we're going to go from 0 to 1 minus x. That's that line right there. And then the x's go from 0 to 1. And so that surface integral, which is just a regular old double integral, is going to give us the work done. I know it's crazy, but that's actually going to calculate the work done as we go around that curve. All right, so I just realized I'm like way over time. I apologize. So I think here's what I want to do. I'm going to stick around and answer any questions on this, but then on Friday, we'll do a couple more examples of Stokes theorem because I don't feel like we're really quite there yet. But questions on this one? Do you see what I did? In general, we're all right.
So when you did, when you got the 2z minus 1, you said it's the dot product of the curl and the unit normal vector?
Not the unit normal vector.
Or a normal vector?
Yep.
Why?
That's how we do surface integrals. When
Yeah,
we did
that's
surface,
true. Yeah, I feel it.
if you go back, look at surface, I know, because now all of a sudden we've got all these different integrals with all the different processes and everything. So trust me, I get it. But with surface integrals, remember that was like kind of like the functional way of how we did it. We're finding the piece that is orthogonal to the surface. So it's a projection onto a normal vector. And the magnitude ends up not mattering because that cancels out. Right? Because you like normally we would go to, we need the unit normal vector. So we would divide by its magnitude. But the magnitude of that is part of the Jacobian, or is the Jacobian, I should say, for the transformation. And so that's why it just cancels and doesn't matter anymore. All right, other questions on that? Okay, so we will revisit this. Don't worry, we'll do a couple more on Friday. But man, it's all coming together. And hopefully you're seeing the whole point of these last couple of theorems is that they allow us to change forms when one form is much easier to do than the other. And when that's going to be is totally just depends. Sometimes one form is better than the other, but it's nice to have those options when we've got them. All right, so with that, I'm going to go ahead and stop recording for today, and I will see you all on Friday.